Hi, hello, good morning, good afternoon, good evening, whatever time you may be watching this. This is still the Great Teacher, and we're back with some new lessons. And for this video specifically, we will be talking about difference of two squares. So let's just jump right into it. Now let's begin with our discussion of difference of two squares. One of the most important things for us to know first before we discuss this concept is the concept of squares. What do we mean by squares? So to start this all, let's have a quick review of perfect squares in relation to integers, or in this case we'll focus on positive numbers, and at the same time a few variables, and as to how can we say if a variable is a perfect square. So let's start with perfect squares as introduced last time when we had perfect square trinomial. I'm sorry, I stuttered in there. So let's have our first example is 1 squared. You can also have 2 squared. You can also have 3 squared. You can also have 4 squared, 5 squared, 6 squared, 7 squared, 8 squared. You can also have 9 squared, and lastly we can have 10 squared. So these concepts have been introduced beforehand when we discussed, or when it was discussed to you, the concepts of exponents, and at the same time with perfect squares. So 1 squared, we know that this could be factored into the, or written as 1 times 1. 2 squared can be 2 times 2. 3 squared can be 3 times 3. 4 squared is 4 times 4. 5 times 5. 6 times 6. You can also have 7 times 7. 8 times 8. You can also have 9 times 9. We can also have 10 times 10. Basically, perfect squares are or numbers whose factors are the same in here, in this case. One of the misconceptions in relation to what does an exponent imply or what it means. For example, the exponent here for perfect squares, or we start with the factor or their root, as for example here 1 is the root and it's raised to the power of 2. That's 1 squared. They say that the exponent tells us how many times we will multiply the number by itself. Unfortunately, that is wrong. Instead, the exponent tells us how many times we will use the base as a factor. Because if you say multiply to itself, like 1 raised to 2, that will be like 1 times 1 times 1. So there's a dilemma in there. The most specific answer is that the exponent tells us how many times we will use the base as a factor. And here we have 2 factors for the base. We use it twice. Well, for the twice people there, for the ones, just kidding. So 1 times 1, that is 1. 2 times 2, that is 4. 3 times 3, that's 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. At the same time, it is also okay to introduce another concept related to perfect squares, which is the concept of square roots. Square roots is basically related to perfect squares most of the time because it will give an exact answer. The thing here is that some students may have or are not yet familiar with this concept, so I'll take this step by step. So to get the square root of a certain number, you can see this, a radical symbol, and the number can be put inside in it. So when you have here, it says square root of 1. So if there's no number indicated here, it means a square root. Basically, there is a 2 here that is not written because it's unnecessary to write it anymore because the name is square root. Square. The concept is a square. So the goal of a square root is to get the square root of the number inside. So the number inside is 1. The square root of this is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. And also the square root of 6 is 36. the same time, the square root of, wait, I wrote it incorrectly. I'm so sorry for that. Let me erase this thing. I wrote 36 here, where it's supposed to be 36 here. This should be 6. I'm sorry. Next is 49. The square root of that is 7. The square root of 64 is 8. The square root of 81 is 9. And lastly, the square root of 100 is 10. But one of the things that is important to be mentioned is that if we have the square root of numbers or integers or even variables, we should consider both the positive and the negative. Because if you have, for example, we have negative 1 raised to 2, that is also equal to positive 1. Therefore, the square root of 1 is positive or negative 1. You will see a symbol like that. This implies that we have 1, the positive, and the negative 1 as the square root or square roots of this given. Similarly for 2, because negative 2 times negative 2 is positive 4, and so on and so forth. So this is the reason why I'm introducing this in this part of the concept as an enrichment, so that you will get used to it when you're identifying the specific factor that makes a number a perfect square. Like for 4, 2 is the factor that you multiply, or the use as the base to raise to 2 to get the perfect square, and so on and so forth. So we can also use the context of square roots to make it much easier to understand. To continue, we can also have square roots or perfect squares in relation to variables. So let's have here, for example, a squared, a raised to 4. Number 3, we can have a raised to 6. For 4, we can have a raised to 8. And lastly, we can also have a raised to 10. This will continue and on and on and on, and you don't have to worry too much. Basically, you can see a pattern already wherein the exponents are all even numbers. So it's an important detail to mention that when identifying if a given variable is a perfect square, the exponent should be in even number. So the factors that makes a squared a perfect square is basically a times a. Here, a raised to 4 is a squared times a squared. A raised to 6 is a raised to 3 times a raised to 3. A raised to 8 is a raised to 4 times a raised to 4. A raised to 10 is a raised to 5 times a raised to 5. The thing here about getting the square roots of the given is not that complicated. Actually, you can already see the pattern as to how you get the factors of given perfect squares when they are variables. So let's say we have the first one here as the square root of a squared. All you have to do is to get or to divide your exponent inside by the square root outside. So 2 divided by 2, that can be the way that you look at it, because again, there's an invisible 2 in this radical symbol. So it's something that you can use. Wait, I'm so sorry for that. This could be positive and negative a. So here, kasi we're only showing the positive factors, just the positive ones, but there are also pairs of factors that are negative that we can use. Here, the square root of a raised to 4. So basically, what's 4 divided by 2? That will give you a squared. And to continue, we'll have some more. A raised to 6. The square root of that is positive and negative a raised to 3. To continue also, a raised to 8. Divide 8 by 2. That will give you 4. So a raised to 4. Okay. A raised to 4. And lastly, the square root of a raised to 10. That will give you positive and negative a raised to 5. So same concept here, different way of discussing it, different way of solving it for it. But the important detail is that for variables, we can say that they are perfect squares if the exponents or the exponent is an even number. So this is a review of perfect squares, both for numbers and variables. And I think this is a long enough review. We can now go on with our discussion of difference of two squares. So we're gonna factor our first set of special products. Basically, the idea that we have established there, the reason why we put it in factored form, because it's important to note that we're using the same numbers as the factors. Like for x squared minus 9, you have a perfect square, which is x squared, and 9 as a perfect square. And from the name itself, you have two squares, and the operation must be difference or subtraction, as pointed out here. Now it looks like a robot. And as you can see, the factors are the same, except for the sign used. One is positive, one is negative. So basically, again, multiplication is the inverse of factoring. Factoring is the inverse of multiplication. So x squared minus 9, the factors are x plus 3 times the quantity x plus 3 times the quantity x minus 3. So if you know your perfect squares, you do not have to worry that much. Okay? So let's start with our very first example, which is 4x squared. So we know that 4x squared is a perfect square because of the number 4 and the variable x squared. We also know that 5 is a perfect square. 4x squared is equal to 2x times 2x. 25 is equal to 5 times 5. Actually, when we're dealing with difference of two squares, you don't have to worry about the negative factors of the perfect squares because there's already a format that we have to follow. So what do you mean by the A and what do you mean by the B? You can look at it like this. So simply write the factored form format, which is a plus b times the quantity a minus b. And remember earlier, the format for or the pattern is a squared minus b squared. So now that we have factored it this way, we can say that one of the factors is a. So a is 2x, and we can say that b is 5. The other way of solving this or talking about this is basically get the square root of the first term. So the square root of 4x squared is equal to 2x. The square root of 25 is equal to 5. So that's it. Your a is the square root of the first term and your b is the square root of the second term. You will still have different ways of understanding it and solving for it, but both are accepted. So once you identify your a and b, all you have to do is to substitute. So one of the things that I've noticed is that students are confused with what we mean by substitution. Substitution doesn't have to be complicated. So when we're doing substitution, it says here a, and a is 2x. Imagine it like in sports wherein one player is substituted so another player will come in. So they are most of the time when we're doing it or the coaches are doing it, they're substituting players of the same play or the way they play. Like if they're both forward, most of the time that's how they do it in sports, like in basketball. Like they should have the same position when you're trading or substituting players for it to not change the way the play is being done. I hope you guys get me with that one. But that's one of the analogies that I can give. Same case with volleyball. The player should have same roles when they're changing. So in this case, a is the same as 2x. So if a here plus b, we can say that we can have the quantity 2x plus 5. And again, don't have to overcomplicate this. This is 2x minus 5. A is 2x, b is 5. And at the same time, this can also be written as the quantity 2x minus 5 times the quantity 2x plus 5. Whichever comes first, all good, nothing to worry about. Okay? So again, I'm showing you here two sets of solutions, but we can still try some more. So let's go with another one. Let's have 16a squared b squared minus 25c squared. You don't have to worry about this because, again, you just have to tick the boxes. Identify first the first and second terms if they are perfect squares. So you have 16, that's a perfect square. A squared, that's a perfect square. B squared, that's a perfect square. We can factor this as 4ab times the quantity 4ab. Same case when you apply the square root of it, you will still get the same answer. For 25c squared, that's 5c times 5c. Always remember, we can only apply this kind of factoring if we are given with the difference of two squares. It's important to pay attention to the minus sign here. Okay? So just follow the format for the factored form. You can have the quantity a plus b times the quantity a minus b. Just use 1 for your a, use 1 for your b. A is 4ab. b is 5c. So this will give us 4ab plus 5c times the quantity 4ab minus 5c. So this is your final answer. And just like earlier, you can go also with the other way around. The minus comes first instead of the plus. When you have patterns like this, you don't really have to worry that much. You just have to remember how to substitute. Okay? So let's have another one. 9x squared minus 1. It's still difference. And these are still squares. So this will be 3x times 3x. Factors of 1 is basically 1 times 1. So our a can be 3x. Our b can be 1. So this will be a plus b times the quantity a minus b. So you'll have 3x plus 1 times the quantity 3x minus 1. Just like that. There goes your final answer. It doesn't have to be difficult. All you have to do is to remember all of your squares, and that's it. If there's a number and a variable, don't panic. Just remember that 9 is a perfect square and the variable x squared is also a perfect square. You don't have to panic that much when you're seeing a lot of things, okay? That's why we had the review earlier. Similarly here, we just change the letters or the variable, but still is a perfect square because this is an even number. The operation is still minus, so this is a difference of two squares. N squared is n times n, m squared is m times m. So you can have here basically n plus m as your first binomial and n minus m as your second binomial. As easy as that. No need to overcomplicate things, class. Okay? So this is your final answer for this one. To continue, you have n squared minus m raised to 6. The exponent is even, same case with the second term. The operation is subtraction. This is dots or difference of two squares. To get the factors of n raised to 10, basically divide 10 by 2. You'll get n raised to 5 times n raised to 5. M raised to 6, divide 6 by 2. You'll get 3. M raised to 3 times m raised to 3. I got excited in there. I'm so sorry. But still, the format, n raised to 5 plus m raised to 3. That's your first binomial. Second binomial is n raised to 5 minus m raised to 3. Remember here, class, the difference between difference of two squares and perfect square trinomials is that PST have the same factors. Like every single thing should be the same. But for difference of two squares, one should be plus, one should be minus. Same terms, different operations. Okay? That's why we have difference of two squares. Let's have some more. Let's have 25a raised to 4 minus 36b raised to 4. So this could be 5a raised to 2 times 5a raised to 2. This could be 6b raised to 2 times 6b raised to 2. I'm sorry for getting faster in here because basically we're just applying the same concepts over and over again. As much as possible, I want you guys to see or try out more examples with me. And yes, it starts complicated, but as long as you follow the rules or know your first 10 numbers, like what is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, if you know all those, you will be surviving the concepts of perfect squares smoothly. At the same time, if you know that the variables are raised to an even exponent and you know that it means it's a perfect square already, you're all good. You don't have to worry that much. And to get the factor that you need, just divide by 2, just like this one, a raised to 4, you get a squared and a squared. That's it. And you can factor this out as 5a squared plus 6b squared. That's your first binomial, and the second one is the same except for the operation, and you're all good. Excuse me, I just ate. This is one is subtraction supposedly. Okay, and again, I'll accept the answer because it's the same thing if it's the other way around. If you start with the minus instead of the plus. Okay, let's have some more examples. Excuse me, this one is 100x squared, so basically 10 times 10, but for the x squared, that's x, so x times x, so 10x, 10x. 81y squared, that's 9y times 9y, and that's it. You can have 10x plus 9y as your first binomial, and the second one is 10x minus 9y. Okay? So now, what if we have this kind of example? We have 8x squared minus 18y squared. You might be wondering, sir, the variable is indeed a perfect square, but the 8 and 18 are not. But here's the thing. Do they have something in common? Yes, they have. If you look at 8 and 18, both are divisible by 2. So we can say that the GCF must be 2. So by doing that, by getting the GCF, divide both terms by 2, you'll get 2 times the quantity 4x squared minus 9y squared. So what we did here is we started with factoring by GCF before we could actually start with difference of two squares. As you can see here, you now have a dots. So therefore, we can factor this out. So this will look like this. 2 times the quantity, the first factor would be 2x plus 3y, and the second factor is 2x minus 3y. So you don't have to panic that much when you see something like this. Just tap into the skills that you have acquired in our factoring from the beginning. So by GCF, you do it, factor the GCF here, and with that, you'll get a difference of two squares, factor out your difference of two squares, and you'll get your final answer. Just like that. And I think for you, especially for my students, you're asking for some more examples. So let's have some more. So for this one, I'll have 10 examples, I guess. So this is for enrichment. So you may skip this or you may go to this immediately if you need more examples. So let's start with a blank page of paper, of slide, and I'll divide this into two. So we will have some basic examples, and we'll also have some average examples. The difficult ones will be for next time because I would like to just have here more enrichment examples. So we can have first x squared minus 1. We can also have, let's say, 4x squared minus 9. We can also have 9a squared minus 25. We can also have here, let's say, 25b squared minus 49. Number 5, we can also have, let's say, 49c raised to 4 minus 81. So the good thing about this one is we haven't discussed this, and you may try it on your own while I'm writing down the items. So for the average, let's say we have let's say we have x raised to 4 minus 16. Can also have here, let's say we have a raised to 4 b squared minus c raised to 6. Let's also have here 3x squared minus 27. Let's also have 8a raised to 4 minus 32b squared. I'm sorry, I cannot read my handwriting. I wrote this on a piece of paper, but I can read it carefully. I write small on paper, but on things like this, even the blackboard, I write big, so please forgive me. But let's have the last one. I'm talking way too much. This one is x raised to 4 minus 1. So, you have here x squared minus 1. You already know that this is x times x, and for 1, that's 1 times 1. So therefore, you'll know already that this is the quantity x plus 1 times the quantity x minus 1. Okay? So that's it. For x squared, you know that's 2x times 2x. For 9, that's 3 times 3. So therefore, you can have 2x plus 3 times the quantity 2x minus 3. Okay? Next, 9a squared, that's 3a times 3a. 25, that's 5 times 5. So therefore, you can get here 3a plus 5. Then lastly, you can have 3a minus 5. For number 4, this is 25b squared, so 5b times 5b. For 49, that's 7 times 7. Therefore, you can have here 5b plus 7 as your first binomial, and then 5b minus 7. Lastly, you can have here 7c raised to 2 times 7c raised to 2. And for 81, that's 9 times 9. So your answer here should be 7c squared plus 9, and also 7c squared minus 9. So those are the answers here. You may check your answers if you got it correctly. Don't have to worry too much about that. Next, let's say we have x raised to 4 minus 16. This is x squared times x squared for x raised to 4. For 16, it's 4 times 4. So this could be x squared plus 4 times the quantity x squared minus 4. Now, there's one thing that I would like for you to look at. Look at this one. We will go back to this example because actually it's not yet done. We'll go back to that later. Okay? There's a reason why I encircled it. Next, let's go with the next one. This is a squared b times a squared b. And this one is c cubed times c cubed. So therefore, you can have here a squared b plus c cubed times the quantity a squared b minus c cubed. Here, just like earlier, you can see that 3x squared minus 27, you don't have perfect squares in terms of the numbers, but they do have a GCF. So factor out 3 first, you'll get x squared minus 9. 3x squared divided by 3, that's x squared. 27 divided by 3, that is 9. X squared is equal to x times x. 9 is equal to 3 times 3. So therefore, you can now write this as 3 times the quantity x plus 3 times the quantity x minus 3. So this is your final answer. Next, similarly, earlier, you also have something here that you can do. The GCF is 8. So this will give you a raised to 4 minus 4b squared. So therefore, here you can have a squared times a squared for a raised to 4. For 4b squared, that is 2b, or not to be, joke lang, 2b times 2b. So this will be 8 times a squared plus 2b. That's your first quantity, and then a squared minus 2b. And for the last one, this will be x squared times x squared and 1 times 1. So this will give you x squared plus 1 times the quantity x squared minus 1. Now, here's the thing. Can you see x squared minus 4 and x squared minus 1? I want you to pay attention to that. What can you say about those two things that I've encircled? So basically, item number 6 and item number 10. The question that I would like to ask is, are they already factored completely? Again, are they already factored completely? And that is something that I will leave for you guys to discuss. I will not answer it in this video because I think it's important for you to remember what we've been discussing and to use your critical thinking skills. Again, the question is, are they already factored completely? And there's a reason why I would like to end here, and probably you know already the answer, but that's the point of this. So it's for you to practice and to understand better. So check out number 6 and number 10. Diba? Sa kayo nakakita, YouTube video nagbigay ng assignment. But yeah, you may try out number 6 and 10. Again, my question is, are they already factored completely? And that will be it. And I'll see you guys. Roll the outro. Roll it. Because I'm stuttering now. Roll the outro. Bye-bye. And that ends our lesson of factoring these specific special products. And now we're getting nearer and nearer to the end of factoring polynomials. For our next few concepts, we will focus on factoring general trinomials and some word problems to deal with. And with that being said, in case you don't hear me or see me, well, good morning, good afternoon, good evening, and good night. Always remember what's up, and it's respect. Peace out. Bye-bye.